So our next speaker is going to be Lu from Argonne National Laboratory, and he has a wealth of expertise in optimizing the electronic structure calculation package QMCPACK for the latest and greatest high-performance computer architecture. And he is going to give us, I think, an evolutionary view on how OpenMP has, is, and will be helping over time. So,
thanks. Okay, I'm Lu from Argonne Leadership Computing Facility at Argonne National Lab. Today I'm going to talk about the QMCPACK application, the past, the present, and the future. So the talk will consist of those parts. So we'll first start with QMC basics and a bit of QMCPACK, the code. Then I will show that how OpenMP is introduced from the beginning of this code. Later is our recent work to achieve performance portability on CPUs via the OpenMP SIMD. Then our new experiments doing the 4.5 offloading to get prepared for the future. So this work is supported by Intel Parallel Computing Center at Argonne. This gives us a lot of help from the Intel engineers. Then this research was using resources from Argonne and Oak Ridge, and this is also supported by the Exascale Computing Project. So start with quantum Monte Carlo basics. Quantum Monte Carlo actually is not a single method. It's basically a set of Monte Carlo algorithms solving quantum mechanics. So QMCPACK is a modern high-performance open-source quantum Monte Carlo simulation code. So it mainly deals with electronic structure calculations. So it can do molecules like 2D systems and also solids. QMCPACK is a C++ code and adopting MPI plus X parallelism scheme. So the X is OpenMP for CPUs and CUDA for the GPUs at the moment. So we are at, you can get more information at qmcpack.org, and our code is publicly available at GitHub. So we get one of the application developer award of the ECP project. So don't be scared, this is the only slide with formulas. So basically what we do with quantum Monte Carlo is solving the Schrödinger equations. When you do the energy of the Schrödinger equation, then it's basically you do the integral, multi-dimensional integral of the Hamiltonian in the real space, and you get the energy. Instead of the traditional method, like quantum chemistry method or density functional method, you do the integral directly. We do it stochastically. Instead of doing integral, so we sample the space using these Monte Carlo techniques and sum up all the samples we collect, and you get an energy with an error bar. It's beneficial because it can be parallelized easily, and you can control the accuracy you need. And so in a lot of cases, actually, you don't need the 7th digit for your calculation, because the method, like the other method, density functional theory, so basically at the fourth digit, usually, the method itself has error larger than that. So this is the difference comparing a stochastic method and a deterministic method. So the random walk, the Monte Carlo sampling is generated by random walking. So it's performed by walker then evolving on Markov chain, and we can employ many walkers. So this is a schematic of diffusion Monte Carlo, slightly different from variational, but it's close in terms of coding and implementing the parallelism. So you have an example of a set of walkers, Then in time you evolve those workers. You do some, you propose a new position, new set of new configuration, then you do the calculations, then you get a few quantities of the new configuration. You could decide whether I accept it or not. The calculation is here. Doing the random walking takes a lot of time. Then once it's been accepted, so you can keep going the next proposed move, that next iteration. In diffusion Monte Carlo, there are a bit more work that the workers can spawn new workers, and workers can be killed if they have a very low weight. It's basically to get more efficient sampling and deal with the load balance. But this kind of communication is small, and we basically say this usually takes less than 10% of the total computing time. So our challenging part is doing the computing quick. So this is a pseudocode of the quantum Monte Carlo algorithm. Basically, you start with a sequential loop, that is the time evolution. Then you have the second loop over the ensemble, that's all the workers. At the fourth step, you have another loop introduced. It's a sequential loop. The reason is in algorithms, when we do algorithms, doing single particle move is more efficient than moving all the particle at once, because once you get one rejection, all your calculation is wasted. So it's better to do single particle moves. This is sequential loop. Then inside single particle move, you do a bunch of derivatives over all the particles, because you move one particle, but the one particle is interacting with all the rest particles. And even in the orbital side, when we move one particle, the single particle orbitals of all the bands correspond to this particle has to be calculated. So you always have an extra loop over the particles, which is pretty big. So it can be in the size of 1K. So with those two major parallelizable loops, the loop 2, the workers can be easily distributed over MPI, and on a node we usually put about tens of workers, which can be distributed over CPU cores or the SMs of GPUs using OpenMP and CUDA. That's why we get almost close to ideal speed up in scaling. And the inner loop, this 6A7 carries, can be easily exposed to the CPU SIMD or GPU thread. So this is the way we use the parallelism on that node. So first show you the worker level parallelism, how we implement it. This is the management of our calculation. So we have those workers to be evolved. These workers actually are the lightweight ones. They carry only the minimum data because, as I said, you need to give birth and kill them, then you need to rebalance, so they have to be communicated, so they must be small. Then you have those movers actually sitting on the thread. So you just do an OpenMP parallel, you have threads and have a mover sitting on it. It holds more data for the scratch during the calculations. So then you just put an OMP4 just to distribute all the worker over those movers. And there's no synchronization at all during the calculation, and before you need to do the next iteration, yes, you have to just do a single synchronization. So it's very efficient on the node with this scheme, so implementing OpenMP. So the OpenMP, there's another reason we use OpenMP, that is to take advantage of the shared memory feature. So actually, during the calculation, those movers need to access the coefficients used for calculating single particle orbitals, that is the B-SPLINE. So it's a trade-off we made, particularly for quantum Monte Carlo, for fast calculation but larger memory footprint. You can think it's you have explicitly localized basis set, so all your calculations gets localized instead of having a huge basis set which increase proportional to the number of system size. So, but this one is big. It's usually at it can go up to 100 gigabytes, just fill the whole node memory. Because it needs to be accessed frequently, randomly, it cannot be, you cannot take the data from a different node. That's too slow. That's for this reason that this B-SPLINE table is replicated on every node. And since it's read-only, so we just initialize once and share by all the movers. That's why we need OpenMP features to accommodate this requirement. So then I'm going to talk about how we'll do the particle level parallelism, the fine level. So the previous parallelism is implemented from the very beginning. We are happy with it since it works for the past 10 years. I think it will keep working. Then when we start to use BlueGeneQ, we notice a few problems. So this is the profile done on BlueGeneQ of all the important kernels. So QMC actually during the calculation we involve several different type of kernels. So the B-SPLINE kernel is like dealing with orbitals. It's more like dense linear algebra. Then the JASTROW factors or distance tables, it looks like a particle code. So this type of calculation, they have distinctive features, but they all have the n particle parallelism can be taken advantage. On those kernels, we noticed actually the numerical light kernels like JASTROW factors, distance tables, they are taking a lot of time, much higher than what we expected. So we were wondering why those are happening. And so for the B-SPLINE calculation, actually we heavily optimized for BlueGeneQ. And all the rest parts, we didn't do that much in the past because this was the dominant problem. Then later, when we just nail this one, then all the other goes up. Then we come to the night landing. We just notice actually those light kernels is getting even worse, taking much higher percentage of the time of the total calculation. So we really need to solve this issue since we can easily use cores, but we didn't do well on the cores. On the efficiency for the cores. So how to improve the performance? So there are two things we did in the beginning of this year. Last year and this year. So one part is we are always doing double precision except the B-SPLINE, which can do single precision. So KERNEL has these features. You have double single precision throughput in the vector unit. We need to use it, and we are sure that it's not the accuracy is not a problem. And then SIMD efficiency is very low in our code. The main reason is we are using a lot of array of structures, like the positions. You have n particles and the 3 dimension. These are good object-oriented programming way, but it's not ideal for high performance for the Xeons or in general high performance computing. So basically we are getting scalar performance out of those calculations. And in the past when we do vectorization, we only did for the B-SPLINE orbitals. So we have the Einstein library which we have the SSE and the QPX specifically for BlueGeneQ, and we have a bit optimization with QPSK in the distance table. However, if you look at the code, I have no idea what are these things actually, unless I have a menu put aside and read it carefully. And the intrinsics for QPX, I can understand it only because I wrote it. But it's still not ideal to read this kind of code for most people. So we first solve the precision. So we bring most of the calculation from double precision to single precision. So you could gain a lot of memory bandwidth on BlueGeneQ and also gain performance on KERNEL. However, the gain on KERNEL is not that great. So it's only about 20% or 50%. Though actually this 55% was gained because we put more things in HBM. It's not because we are doing calculation more efficient. So clearly this problem is coupled with the vectorization, because if you have a scalar you don't have vector performance, you have scalar, doing single precision, double precision should not change that much. So we really need to handle the performance of vectorization and handle both double and single precision. So we focused on the vectorization from the beginning of this year. Actually, our paper was accepted to SC and it's already on archive. So what we design is to do the vectorization. Since doing the vectorization, we need to change the data layout in several very fundamental data structures. This potentially will pollute a lot of codes. We would like to have minimized changes. This is for the old code part. For the newly added implementation, we have those requirements. Vector single source, both precision types, no more intrinsics, hope to have any vector length, any alignment requirements, any compute compilers, and any CPU vendors. Actually, we made it. So what we do is via several tools. One is the C++. We use templates. So when you use templates, actually you can deal with those types easily. Then we use operator overloading with it. The old code, we can provide the operator function serves as the old purpose. So these you don't need to change that much. Then in C++ class, you can also handle the alignment. So with OpenMP 4.0, actually we have this SIMD construct with aligned clause we can use. So this is actually what we do to change the data layout from array of structures to structure of arrays via this adapter class, this container class, sorry. In this container class, you hold the data with aligned vectors. So you have, basically we just change the STD vector with a different allocator. I really hope a C++ standard can provide directly an aligned allocator. C has it, then we have to wrap around it. Then you get this aligned vector holding the data, which is size of n multiplied by d is the dimension. Then we provide an access method, this operator overloading, so you can return the old structures easily, so backward compatibility. Then we provide access method. You can get the, if you have 3 by n array, then you can get the third n array or second n array just by calling this one. So in the old data, in old code we have those vector of this tiny vector, that's a small array of 3. Those data types for the particle coordinates, gradient, Hessian. Actually now we just do it with a new class. And for the old codes you don't need to change at all. Then alignment is just handled inside this. So we have those parts settled. Then in the computing part, so it gets more clean, no more intrinsics, as I said. So now when you do the calculation, you have a loop of 3, which loop over the 3 dimensions, not 3, x, y, z. Then you basically extract the pointers, do your calculation with a single loop, then you put OMP SIMD. Then you put a line indicating those variables are all aligned, but you don't need to specify the alignment, the size. So, okay. So it's in this way it's very flexible to the vector length. On BGQ we have like 256 bits. KERNEL you have 512. On AMD you have 128. So that all can be handled by this single pragma, super clean, and it's all vectorized. You only see vector load, vector store in the assembly. As a scientist, I'm willing to change the algorithms, and it helps a lot to vectorize the code. So in QMCPACK, before, when we do the JASTROW calculation, we have a two-body potential. Actually, we store the whole matrix. When we propose a move, you just compute the scratch state of this proposed move, and if it's been accepted, you have to update one row and one column, which is clearly not efficient for memory. But actually, for the calculation, you only need the summation of this potential over J. So you only need the summation of a row. That's why I change it here. So it becomes just a column of summations. Now what you do is you do an update algorithm. When you propose a move, actually you update those summations by subtracting the old value and add back the new value. And for this particular moved particle, you just put the new value directly. That makes the numerical very robust. So with this algorithm change, you will find actually we are always dealing vectors. So perfect. So with this change, actually, you also save a lot of memory for in the JASTROW factor, which clearly we don't want for these cheap cost kernels. And we can give more memory to the splines. We really care about big systems. And also on KERNEL system, you fit the SPM and you gain performance clearly. So by those SIMD optimization and algorithm change, actually, on those kernels like J2, the two-body JASTROW, the distance tables, in this roofline analysis, I don't know if you are familiar with roofline analysis. Basically, if you go that direction, it's the ideal direction. So you get flops, and then the memory access is less frequent, and you gain a lot of performance. So we basically, you see the breakout of different kernels in the reference code and the optimized code. There's a huge reduction, and we basically gain a factor of 2x across most platforms. So this is a benchmark we did on several system and system sizes. Like this is the largest calculation, and on different processors. BlueGeneQ, the very old one. Actually, we are happy. We are still running the BlueGeneQ, and we are happy that we gain a lot of performance also on BlueGeneQ. Because Excel doesn't provide new compilers, but the client has. Then we have the Broadwell and KERNEL, so they all get significant boost in performance with our optimization. So just a quick summary of the previous parts. So OpenMP helps us, the shared memory helps us to solve the memory issue of the big B-SPLINE table. It expresses our on-node parallelism, including threading and vectorization. It enables us to write very clean and understandable code, and it gives us perfect thread scaling and SIMD efficiency. And how about accelerators? So we start to experiment OpenMP offload to the accelerators. So why we need to try this? So in the past, QMCPACK actually, as I mentioned, has OpenMP and CUDA. So internally in the code is like two big forks, and they are largely incompatible. Apart from the initialization, maybe some I/O, they're the same, and the input file maybe is the same, but internally in the computing, they are like two giant forks, and it also makes us not. It becomes not possible. We can never provide an easy fallback solution if the implementation is missing on one side. Usually it's the GPU side. That's why the GPU features much less than the CPU code. And we are always lack of the developers, and especially hard to get someone knows both and get double the time to implement both kernels. So in long term, we really need a portable solution. And we don't like to depend on proprietary solutions, and portable performance is desired. So for performance portability, we'd like to assess the capability of OpenMP under those criteria. It needs to be run on both CPU and GPU. So first is the capability. Can we express our required concurrency with OpenMP? And second, is the performance good? And portability, what is the extent of required changes to make them running well on both architectures? And how about the compilers, libraries, and tools? So we don't try it directly on QMCPACK. It's too much workload. Mini QMC. So during our structure array optimizations, we developed a set of mini apps specifically for QMCPACK. They are standalone, means they are separated from the whole QMCPACK. Yeah, they are separate from QMCPACK for this specific purpose. The code actually expresses the same concurrency as QMCPACK, so all the parallelism levels are placed there. And they use the state-of-art algorithms, so all the legacy algorithms we have on CPU, or the legacy algorithm we all have on GPU, we just pick the best one. They're designed to collaborate with non-QMC developers, and it will be public on GitHub by the end of this month. So it's one of the deliverables for the ECP project. So here I'm going to talk about, I tried offloading things on this 3D cubic B-SPLINE kernel. This kernel is, the characteristic of this kernel is it's a bit memory bound. So QMCPACK, as I mentioned, they have many kernels. Some are memory bound, some are compute bound. This one is memory bound. So I start from the mini app, this original version. So the two-level parallelism is I wrote them separately on the left and right side. So basically, this side you have a parallel for over all the workers, just to mimic the worker parallelism. And this is the computing of a set of spline orbitals, and we have the OMP SIMD I mentioned earlier. So let me see. Yeah, so this deals with a single worker business. However, in this implementation, you might notice there's inner loop IE there, which is sequential. So on CPU side, it's okay, but on GPU side, it's a problem. That's why in the QMCPACK pseudocode I just repeated here, in the GPU implementation, the loop 2 and 4 are interchanged. So the sequential loop is bring out, the worker loop is bring in, and then they can be launched within a single kernel launch on the GPU just to gain efficiency. So what I do for the offloading to the device, how many minutes I have? Oh. Okay, good. I think I can do it. This kernel, the first change to the V1 is to interchange those loops. So I bring this electron single particle move loop out and bring the worker loop inside. So by this change, you actually need to prepare those scratch data just for collecting the result for all the workers. Then I add back those target pragmas. I still left the OMP parallel for this so the blue ones are for the CPU. So when you run CPU, you have those pragma. Then when you run GPU, you have those red pragma. Yes, so they're slightly different. I'm not using a single pragma just to make sure I get good performance. And the compiler is doing what I told them exactly on different devices. So basically, in this implementation, this becomes a single kernel launch on the GPUs. And I did a bit more. So the data mapping is a bit painful. I don't want to do it everywhere. And since the vector type in QMCPACK is a major type, vector or SOA vector, it's a major type, so I just do an OMP vector. Just found part of them is found on the tutorial. Based on the derived from the base type. Then what I do extra is during a resize, I do the enter data mapping, just mapping the data pointers. And then I just implement those up to device, update from device. If you really need to do that, in QMC implementation, most calculations on GPU, so you don't need to back and forth send data. But like I do a mini app, I need to check the results, so I have to copy the data. So you implement those helper functions and hide all the details inside. And then the destructor, you just do the exit data. So this, in the code, basically you change the data type from a vector type to an OMP vector type. And for glue, so since I'm gather the workers and launch a single kernel, I need to collect a bunch of pointers and do the deep copy to the device. So I actually can reuse this data type just to collect the pointers, and also save me a lot of lines of code. I'm quite happy with this kind of hiding things. Yes, so we have the CUDA code, and I know the CUDA code. So I was thinking, what was exactly the CUDA code doing in terms of implementation details? So I was thinking that, I see that there is a kind of loop interchange in the CUDA implementation. The major change is the spline calculation is, sorry, I missed one thing earlier. The spline calculation, okay, let's look at the spline calculation details. So it's XYZ three dimension. Then you get 4 points in the X, you do interpolation for the position you want to calculate, Y 4 points, Z 4 points. So I write this simple XYZ loop, IJK loop for the 64 points in total spline interpolation. And the innermost is the loop over all the bands. So it's the size is the number of electrons. So it's a very large loop. This one fits very well on CPUs because these data are all in cache. Then it's just streaming to the vector unit and do the computing. So it's efficient on the CPUs. But however, on the GPU side, usually we know that writing back and forth to the global memory is a bad thing. So that's why I decided to do this change. I move the loop out, the innermost loop out, just create a local variable, just to do a temporal one, and do the computing reduction. Okay, the reduction just on this. Sorry, I didn't write the plus. It should be plus equal those. So you should do the. I do the reduction on this temporal array, and the end just write back the result. So this is more close to the GPU. So here we look at the performance. So to gain on the CPU from V0 to V1, because the goal is to gain to reduce the kernel launching overhead of the for our target region. So we need to fuse the workers into a single core, to a single kernel. So, but however, this will require more fork join synchronization on the CPU side. So I was checking that how much performance we lose. Just weird, there's a shadow next to it on the CPU. So for this small size calculation, actually on CPU side we lose a bit performance. Then we run this V1 on GPU. Oh, the performance is not nice. It's much slower compared to the CPU. Oh, okay, by the way, it's doing on the Power 8 and Pascal. CPU means Power 8, Pascal is the device with the client compiler. So then I switch to the V2, and clearly I lose performance on the CPU compared to the V1, but I gain performance on the GPU, still not very satisfactory. So then I see, let me see medium size, maybe because my workload is too light. Yeah, it actually changed quite a lot. So the functional overhead seems gone, and it seems that V1 could run as fast as V0 on the CPU side. Then the GPU performance of V1 is still much slower than the CPU version. However, when I change to the V2, actually the performance now goes much better than not much, better than the CPU, the reference performance. So, yeah, sadly, now we have one version good for CPU and one version good for GPU. So, I start to look at the details of this code, especially because when you do GPU, you know that it's really important to look at the register per thread count and also the occupancy. So what I found is, unfortunately, the register count is high and occupancy is low. And we have the CUDA kernels, and it's about 50 register used. So I think there are improvements we can do. And clearly on our CUDA implementation, we use shared memory to hold the GPU shared memory to hold the kind of constant and constant data and fixed size. So in the CUDA implementation, that way saves the GPU, the registers. But unfortunately, we could not do it. At least for the moment, I don't know how to do it. And I could measure the DDR bandwidth. So high bandwidth memory on GPU is the DDR bandwidth when you read the metric. So I'm only getting 80 gigabytes per second, and clearly it's very low at the moment. I think this problem is correlated with low occupancy because you could not parallel launching more requests to the memory to get the data. So I think we can still work on these aspects to improve the performance. And the single source with portable performance is not achieved at the moment on this kernel. I hope the compiler can do some loop reordering, this kind of things. Maybe it's too challenging, we will see. And the compiler quality is improving over time. It takes time. I think as application developer, we can find more bugs and help the developer, the compiler developer to improve the compilers. And I would like to have more accessible information via compiler optimization report, so I don't need to deal with a black box. For the moment, the performance tools, I think is only MV-Pro, so I don't know if there are other. Yeah, this is near the last. Okay, perspective. I still strongly believe in OpenMP. In the following months, I will try more kernels to do this OpenMP offloading, and I will try the other compute-bound kernels. Then we will have more understanding of the current situation in terms of performance for OpenMP. And there's a practical reason to solve the issues I mentioned earlier. So I follow this 80-20 rule. So 80 routines takes only 20% of time. So in the old way, we have to write CPU code and GPU code. And the GPU code is needed only because we don't want to move the data back and forth. We don't really care that much about performance. So if we can write in OpenMP in a single source, that's great. I mean, we don't design much on those. For the 20% routines taking 80% of time, we really like to have performance portable code, but to be reality, if it's really too hard, we could do a minimum architecture-specific code. Okay. Yeah, thanks everyone.
Excellent presentation. So you answered most of my questions and your thoughts already. Do we have any questions? Sure.
I was just wondering how limiting you mentioned that the spline coefficient is work on the node, because it has a lot of data. You kind of replicate that on each node. I was just wondering how limiting is that when you run simulations? Is that not a factor? You want to run a much smaller number of nodes for your calculations, or?
No, it's relevant to the number of nodes. It only cares the per node memory. The memory on the.
Is it a global data structure?
No, it's replicated, exactly replicated on every node. It's all the same on every node.
But you said that it was taking the overwhelming majority of the memory.
Yeah, on a single node. Yeah. It's not worth to distributing them because the access pattern decides you need very fast access, and chunk of data is always small. So.
So will the unified memory help you in this case? Not replicating data. I mean, kind of things.
So the spline data, yes, we would like to have. So on the current GPU code, I implement the UVM, Unified Virtual Addressing, which is kind of slow but makes my science going. So it's still good. I mean, it's from you can run to you cannot run is just infinite speed up, right? Then in terms of performance, yes, it's not great. So the unified memory, I think the CUDA 7 or 8 one, not the old one. Yes, it will help us. I think for the current technology, for the NVLink, the performance should be better. So, however, if we really need the performance, I think I can do more than unified memory. I can, for example, with this V1 to V0 change, we fuse all the workers. Actually, we can do more smart things. We can even, since the JASTROW part doesn't care about the spline coefficients, so we can actually stage the spline coefficients before the calculation while the GPU was busy with the JASTROW factor calculations. Then you just launch, when the data is arrived, you pack this data and launch it. It's way faster. So it really depends on what you need, a lazy solution or ultimate performing solution. Yeah. But I think a lot of easy things like data mapping, small data movement, yeah, it's definitely, I don't want to care. I don't want to maintain or explicitly control them. Yeah.
I just want to, if there's no more, I just have one quick question for the CPU part all the way back again. You said one of the things that OpenMP helped was reducing the memory, or taking advantage of the shared memory with OpenMP. And I was wondering if you had experimented with shared memory Windows or NPR.
Oh, you mean MPI shared memory? No, we are not doing that at this moment. We have some considerations, yeah, for the bigger spline table to put it on a few close-by nodes. Okay. But somehow, as I said, you need to manage the data manually, so you have to be careful. So these different organisms have different purpose, now are entangled. So it's just take a time to figure out one by one.
Okay, well,